Okay, well, we can extend this conditioning, let's call it, to n events. We just write probability of the intersection. I'll just write it this way with dots. This is the intersection of n events. It's just the probability the first event happens times the probability the second event happens, given the first happens. Now what do you want? Probability the third happens, given, well, now I have these both happen. So given the probability E1, E2 happens, and you can build it up this way, probability E4. So these are all multiplied. Sorry, given E1, E2, E3, dot, 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 probability En, given E1, En minus 1. Okay, so you could just keep going like this. For example, in the previous, from the previous lecture, suppose we want to find probability of that, say, first ball red and next to black. Well, we could just write this like this, probability using, so you have to watch the previous video, but just using, say, probability, this would just be R1, B2, B3, right? Something like that. And this could just be PR1, PB2, given R1, and PB3, given R1, B2, which is very natural to do. It comes right from the problem, right? So remember there were 4 red and 2 black, and the subscripts mean the draw. So what do we have? Probability of R1, 2/3. Probability of B2 given R1, said 2 blacks out of 5 balls, so 2/5. Probability B3 given R1 and B2. Now there's only 1 black and there's 3 reds, so 1/4. So we could just do it like this. Maybe it's much easier, so you get 1/15. All right. Okay. Now, though, is the real power of this, I think. We're going to see that if we can find a decomposition of the sample space, that often we can use intersection. We can take intersections of a desired probability with that decomposition and not affect the event. Well, let me just do the example, I think, and then but then I can go from the intersections to computable conditional probabilities. So this is really the power of this, I think, one of them. So suppose an insurance company, this one's in the book, I think. I'm using the same numbers too. Categorizes customers as in one of 2 categories, as A, accident prone, or not. We'll just call this AC. Okay, so either you're accident prone or not, and they model this with, they assume PA equals 3/10. Okay. Okay. Also, they also have PC, probability a policyholder files a claim given they're accident prone is 4/10, and the probability they file a claim given they're not accident prone, drops to 2/10. Okay, you can think of this as a model based on data or just given to you and you're asked to solve the problem. All right, well, the question then is, so we assume these are true. That's what I mean by model. So, question. What's the question? What do you think we want to ask? All right, what's the probability that a random person files a claim in the next year? Okay, yeah, let me write what this is. C means this person files a claim in next year. Okay, in the next business year. So question, what's the probability a person is selected at random find probability they file a claim. So find P of C for a randomly selected person. So C is really a randomly selected person. Okay? Randomly selected person files a claim in the next year. So find P of C. Then I can take it out here. Another way to say this is you can think of it with probabilities. You really want to think of it this way, like you're randomly selecting a person. What's the probability? But another way to think about it is out of the whole population, what percent of the policyholders will file a claim? In essence, it's the same thing. Although it's not either, but it is. So I mean, the language is the same either way. Okay, but let's stick to this. So C is the event that a randomly selected person files a claim in the next 365 days. A is the event that a randomly selected person is accident prone. Okay. So I wasn't very clear about that. A, randomly selected, equally likely person is accident prone. Okay, and then P of A, the probability if I randomly select a person and they're accident prone is 3/10. Probability that if I take all the accident prone people, or that if someone is accident prone that they file a claim, that's 4/10, etc. All right, so what's P of C? So we can do it this way. Probabilities a randomly selected person files a claim. I can say this is P of CS, which is just a technical step. It doesn't really mean anything. That's still just PC. And now I could say decompose S into the people that are accident prone or not accident prone. If you like, you can write S as the union of that a randomly selected person is accident prone or not accident prone. Same thing. This is the probability CA union CAC. These are mutually exclusive. This is PCA plus PCAC. And these, maybe it's not quite clear how to compute these, right? But here's where I can use the conditioning. Okay, so this is my conditioning step. And I know the probability they file a claim given they're accident prone. I'm not sure the probability they're accident prone given they file a claim, so I want to condition on A and on AC. So this is probability of C given A, P of A, conditioning on A, plus P, C given AC, PAC, conditioning on AC. Now, I know everything now, right? What's P of C given A? Well, this is given in the problem. If they're accident prone, it's 0.4, right? So it's 4/10. Probability of A, 3/10. Plus, what's the probability if it was 2/10? Times the probability of AC from complement, it's 7/10. So total answer is 12 over 100 plus 14 over 100. I get 26 over 100, or 0.26. Okay. All right. Now, I'm trying to think if I could do this in 2 minutes. I think we'll just stop. We'll go to the next video to see the next one.